Hello and welcome to another video on Orbital Mechanics. Still going through the book Orbital Mechanics for Engineering Students. I'm up to problem 3.2 and going to do 3.3 as well. These are pretty simple questions really if you've been following the book. They involve finding the roots of equations using the Newton's method and the bisection method. So I'll just get on with 3.2 and you'll see how it goes as we go along. So 3.2 is find the three positive roots of the equation 10 times e to the power of sine x equals x squared minus 5x plus 4. So just write that down. 10 e sine x equals x squared minus 5x plus 4. And to find the roots of this using Newton's method, we have to get the derivative of this. So we're just going to move everything to the right hand side, and so that will make it equal to 0. So 0 equals x squared minus 5x plus 4 minus 10 e sine x. And then we take the derivative of that. That is 0 equals 2x minus 5 minus 10 cos x e to the sine x, exponential to the sine x. That is taking the cosec derivative of sine x down to here. And we lost the 4, 5x becomes 5, x squared becomes 2x. Then we will go to MATLAB and we will solve using the Newton's method. But first I'm going to go on to 3.3 and get the derivative for that equation as well, which is basically the same thing, but for tan x equals tan hyperbolic x. So we'll just do, again, 0 equals tan x minus tan x, and the derivative of that is 1 over cos hyperbolic x squared and then minus 1 over cos squared x. It is actually sec, which is 1 over, so it's sec squared x, which is 1 over cos squared x. So that's that, and then we will pop over to MATLAB and I will show you my algorithms for getting the roots of these equations. So here we are in MATLAB, and I have a simple program that starts at minus 10 and iterates up to minus 20 and searches for the roots of the equation. And it just has so I have two functions. I've got the bisect method and the Newton method. The bisect method takes the function, your starting position, sort of a left position and a right position, and around the answer. The functions are down here. So this is our 3.2. This is the function given. This is the derivative, and this is 3.3, and this is the function. This is the derivative. And if I just run that, so this is, I'll run 3.2 bisect method, you can see I get these 4 roots. It asks for the 3 positive roots, it's those. If I change it to the third, 3.3, you see we have we have 1, 2, 3, 4, 5 there, positive roots. Actually, it's missing this one just because of the, I think the interval that we've got going on there. Yeah, so it's sort of, the bisect method is probably going in one direction there, so it's, I'll just show the, so this is 3.3, and this is the graph for 3.3. You can see we have 0 is at 0, at 4, at 7, and interesting that just doesn't find it directly at 4. It's probably because I'm landing directly on 4. Yeah, that's probably why, and then it's going to 4.5, so I'm not really looking at it over that point, so probably, yeah, I need to do something like 0.5. And then this goes slightly over 1, and that'll find it. There you go. That's all of them there. 0, 3, 7, 10. And I can do the Newton method as well. So that finds them as well. Let's have a look at these functions. So let's start with the bisect method. And starts off, we set an error range. And then we've defined a recursive function called bisect method recursive. And the first thing it does is it gets the midpoint on the x and then gets the y values for the midpoint and one of the endpoints. First check if we've actually got a 0 or if we've got to the end of our bisection and found nothing. Else if b and c are on one side, by and cy are on one side of the y-axis, then we'll do a and b. If we're on the other side, it'll be b and c, and then repeat until we find something. It's quite simple. And then the Newton method is similar structure. Define our error, define a Newton method recursive. We're first going to get our first y value and then a first derivative y value. Then we're going to get a ratio of y over dy. If that turns out to be division by 0, just shift it a little bit and get another ratio, so at least it's a real number. And then run the recursive function, get our x1 from x minus the ratio, get our y1 from the x1. Did we find a 0? Did we find a 0 that's very close to 0? We may actually be on a very thin section, so I was figuring that here it actually finds multiple roots on that line because it's very close to 0 for quite some time, so just because of precision and the error range. So just check the other side of it. If we're very close to 0 and we're on both sides of it, we can assume that it is actually at 0, so just snap it to 0. If we're actually getting bigger here, so if we're going the wrong direction, if we've gone too far, then let's go half the way and see how we do. Else just keep going with our Newton method, taking the next and then getting the new ratio and repeating. So that's it. It's interesting to look at how these functions work. As you can see that this one is it's got lots of 0 gradients. So if we bring up the derivative of that, we can see where it hits 0 down here is actually these points where the gradient is 0, because the derivative of a function is just the gradient. You can see all the overlaps there, and it's the same for this one. The only 0 for that second one is 0. So, but you can see there's no points on here which have a gradient of 0, so you don't get a point with this on 0. The purple one doesn't touch 0 for these points, because you can see it doesn't have a 0 gradient. So that's it for those two questions. Thank you. Goodbye.